Hello.
Hello, how are you?
Good, you?
Good. So how'd your quiz test go?
It was okay. It's okay.
Yeah, it was just okay.
Yeah.
Okay, I will take your word for it then. Okay. All right, well, what are we doing today?
Lewis structures, formal charge, line drawings. We can start with bonding. Let me share my screen.
Ah, line drawings. My favorite. No, for reals.
Oh,
Oh, okay. So this, you just have to look at the charges based on their periodic table, where they're located on the periodic table. Right?
yeah.
So what is, yep, look at bromine.
Oh, you just look at where the. Oh,
Yep,
okay.
and that's -1, right?
Yeah, yeah.
Yeah, that's hella easy, no big deal. Yeah, okay, so you always have to have a positive and a negative, right? A cation and an anion. Helium
Yeah.
and hydrogen are both non-metal, so you can't have that, right?
Uh,
Ionic bond, you always need metal and a non-metal. You can't have two non-metals, right? And then nitrogen and oxygen are also non-metal, so that's covalent and not ionic. Sodium, potassium, they're both metal, so you can't even have any type of bond. Lithium bromide, that's a cation and an anion.
Wait, so ionic is cation and anion?
Yeah,
Wait, how do you tell if it's a cation or an anion?
because you have to look at the screen. Look at the periodic table, I mean, not screen. You know what I meant.
So it's a metal and a non-metal?
Yes. So do you see here? Hold on. Don't move. Okay. This and this are metalloids, right?
Yeah.
Okay. All of this are non-metal. So these are all going to be negatively charged. Okay. Everything here. Actually, not there. These are metals. So these are positively charged. Yeah. And you know these are all +1, +2, +3, minus, I go. Plus or -4, this is -3, -2, -1, and this is 0.
Mhm.
Okay, so lithium is right here, which is a +1, and bromine is right here, which is a -1. So they're metal and non-metal.
Oh, okay. So that's an ionic bond.
It's an ionic bond.
Wait, what is lattice energy?
Lattice energy is the amount of energy needed to break an ionic bond. So ionic bonds are going to look like this. They are made into these things called unit cells. Okay. Basically positive, negative, positive, negative, So there's an attraction like this, okay, and like this, and like this, okay. That attraction is called, it's so strong that it has a special name, and it is called lattice energy. In order for you to break that, lattice energy is dependent upon the charges of each of the ions over the radius squared.
Wait, what is this? Q1, Q2 over R2?
They are charges of the ion. And
Wait, what is this that it's telling us it's S?
that's ionization. Ionization is just when you have like NaCl, it's splitting into Na plus and Cl minus. That's all they're saying here.
Okay.
It is the amount of energy needed to break that in the gaseous state. Oh, your friend is so smart. So these are diatomic molecules like hydrogen, oxygen, nitrogen, chlorine, bromine, iodide, fluorine. So I memorize it as Hunkelbrief, but you can memorize it whatever way you want. Some people memorize it Brinkelhoff, Hunkleberry Finn, whatever floats your boat. But just remember that these are never going to be by themselves. They are always paired up. They're always, always, always paired up.
With itself? Or
With itself, yeah. This is how you find them in its atomic state. So you never find them differently. Like, you know, like sodium can stand by itself, like, or copper, you can find it like that. But oxygen, you will never find it as just oxygen. It's always going to be O2.
Oh, okay.
And oxygen is double bonded, nitrogen is triple bonded, everything else is single bonded.
Okay.
These ones you just have to memorize the polyatomic ions. Have you memorized them?
No.
Shame.
I'll probably just Google it.
You what?
I'll probably just Google it.
For the exam?
Yeah, it's like open Google.
Oh, it is?
Yeah.
Oh my god.
Yeah.
It open Mickey.
Sometimes on Chegg, there's like people asking the questions like, someone answer this, please.
On Chegg?
Yeah.
That's awful.
Yeah, it really is.
What are you guys gonna do later in life?
No idea. People do really bad in class.
Oh. Like seriously, what are you gonna do when you have to take your MCATs and stuff?
I don't know, but people cheat in honors classes, like nobody cheats, but like in these big classes, like everybody's fucking cheating.
That's crazy.
Yeah.
That's really crazy.
There's a question I was looking for. Hold on.
Well, you got a 30 out of 30, Ethan.
I Frank got a 30 out of 30. I don't know about me.
That's so funny. I actually took a pre-quiz today, and I got 10 out of 10. And I ended up taking the post quiz after taking all of the lectures, and I got a 7 out of 10.
For dental school?
What?
For dental school?
Yeah.
Oh my god.
I don't know what that means. I think the professor did a horrible job at teaching me.
Yeah. Can't find it. We can just move on to the next thing.
Okay.
Did we finish? Oh, I'm stupid. Bonding. Yeah, we finished.
It was cell structures.
Yeah.
Okay. Do you understand what a resonance is?
Isn't it like you can have multiple structures of the same thing?
Yep. So like for instance, ozone looks like this. Okay. So who's to say that that double bond has to be on the left side, right? It means it can actually look like this too. So basically what they're trying to say is that this second bond spends half the time on the left side and spends half the time on the right side. But because we can't draw this in animation, you know, because unfortunately we are still in a 2D world, we draw resonances. We show all the possible structures for that particular double bond or that triple bond. So it's always, so the definition of resonance means delocalization of pi bond. And pi bond is the second or third bond. Okay.
So it's not like a double or single bond?
So that's what I mean. It's like the double or the triple bond.
Because there was a question, is there a difference? Because there was a question that was like, how many pi bonds does this have and how many single bonds does it have? And then how many single bonds does it have and how many double bonds does it have?
Yes. So since Ethan likes shortcuts, single bond is just sigma, double bond is sigma pi, triple bond is sigma pi pi.
Okay.
So how do you draw carbonate? It's supposed to look like this. It can look like this, or it can look like this.
So when you have the 2 minus, you just put it in brackets at the top. You don't do anything to the
Yeah.
structure.
I mean, you can, but what it is, it's like you would actually just put it like this.
You
Yeah.
have to. You just put the.
You don't have to. You can just put brackets and put a 2 minus on the outside.
Okay.
How do you draw a nitrate ion? You probably don't even know what a nitrate ion looks like formula-wise, huh? Shame on you. Looks like that. And it's the same exact thing.
Wait, why can't you make triple bonds?
You don't need it.
Wait, what do you mean?
Because you don't need it. So there's 5 electrons here, 3 times 6 electrons there. I always keep forgetting that you have no basis. So there's 24 electrons, right?
Yeah.
We have nitrogen, oxygen, oxygen, oxygen. 1, 2, 3. So how many electrons have we used up?
6.
Good. So how many do I have left?
Wait, where'd you get the 24? Oh, nitrogen has 5 and oxygen has 6.
All the valence. Yep.
Oh, okay.
I have 18 electrons, right?
Yeah.
Nitrogen, is it happy right now? It's got 1, 2, 3, 4, 5, 6. Is it happy?
No.
It's not happy. How many more does it need?
2.
2 more, right?
Yeah.
So minus 2 electrons, so that means I have 16,
Oh, okay.
right? So that's 16 electrons. And then from here, how many electrons does oxygen need?
8.
Yep, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, but I don't have enough. Do you see how this one I don't have enough?
Yeah.
I've used up all 16 electrons. This is why we get rid of this and we put it right there and we make that double bond.
Wait, how do you tell which one's the central atom?
Usually the first atom is going to be the central atom, except for hydrogens. Hydrogens are never the central atom. So whichever comes afterwards is going to be the central atom.
So carbon is the central atom?
For this one, yeah.
Wait, why can't that ever have resonance? Oh, because you can't put the triple bonds.
Yeah, because hydrogen can only have one bond. It doesn't have enough electrons to expand to 2 or 3 bonds.
Okay. Ooh, how do you draw this? In a line draw?
Yeah, so usually this CH3 is this. This CH is this. That CH is this. CH2, and then the Br, right? But here's the problem. Every carbon likes to have how many bonds?
4.
4. But look at this carbon. How many bonds does it have?
3.
And same thing with this one, right?
Yeah.
So how are we going to make up for the lack of that one bond?
Oh.
Yeah.
Wait, don't you not draw carbons and hydrogens though?
You don't have
Isn't it
to.
like,
You want to do stick figure?
because I think that's what they want us to do, because it says we do not draw any CH.
And that's this. The way you do this, it's like this. This is 1, 2, 3, 4, right? 1, 2, 3, 4. Okay.
There you go.
What do you want?
This
Oh,
one?
this one. You do have to draw the NH. But there's no hydrogen, so I think it looks like this.
Wait, how'd you know to put triple bonds? Because they all have to have 4.
Yeah, both carbons have to have 4.
Okay. Wait, how come you don't? How come you do draw COH atoms?
I don't have to.
But there's a choice. It says that they're not implied. Oh, is it because it's a nitrogen?
Yeah. I don't have to, but you can draw it like that if you want.
Aren't there some that you don't draw the hydrogens at all? Because one of my old teachers would just draw lines like without
That's
hydrogen.
only for carbon molecules. Yeah.
Damn.
How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 carbons, right? And then how many hydrogens? That's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
Wait, what about that one? And these two.
Well, this one has like 1, 2, 3, 4 bonds, right?
Yeah.
This one has one.
Oh, so they don't have hydrogen?
18. Which one? Yeah, they don't have hydrogens.
But this one does.
Yeah.
How'd you know that they're? Oh, because the N is here. So it's okay. Wait, so what does this look like? Like, can you draw this in line structure? Like with
This is the line structure.
Oh, like how you drew it? Like how you drew it with the H's and C's showing?
Oh, you want me to draw it with the C's and H's? Like that?
Yeah. Oh, okay.
Yeah. My beautiful drawing.
Wait, so these are all C's?
Yeah. Every single dent is a carbon.
Okay. And these are double bonds?
Yep.
Wait, can you just say this is um like 6 benzene and like an NH2? Or you have to do the whole thing?
You would have to do the whole thing. Okay. And then for hydrogens, 2. These are not benzenes.
Oh damn. Guess I don't remember any of high school.
You have to count every single one. Like that. $15.
Wait, so each C has to have 4 bonds on it,
Correct.
and if there's not enough, you just make up H's.
Correct.
Okay.
So CBr2F2. Do you know how to do formal charges?
Yeah. Number of valence electrons minus number of bonds minus number of like electrons on the atom.
Lone pairs, yeah. So the group number, right, which is 7, minus number of bonds, which is 1, minus number of lone pairs. Or not lone pairs, number of electrons. And there's 1, 2, 3, 4, 5, 6. Right? And this carbon, the group number is 4, minus it's got 4 bonds, minus 0 electrons, so that's 0. Bromine is also 7, minus 1, minus 6.
Okay. Does this have a double bond? Or
Yeah.
do you put it? Uh, how do you know it's not like on the bromine?
Oh, I know because I've done this so much. But think about it. If you do it on bromine, you're gonna have to do it on the other bromine as well.
I guess.
You need to usually bromine likes to have 8 electrons. I mean, bromine likes to have 7 valence electrons, whereas oxygen only has 6. So oxygen is the one that's kind of missing.
So you never put like a lone pair on the central atom?
Carbon, it's blasphemy if you were to have a lone pair on carbon.
Okay.
And you'll learn more about this later on when you're taking organic chem, but just kind of keep it in mind that you don't ever want to have something like that. And
Okay.
that's why you do formal charges. If you do it like this, it's going to give you a different formal charge than if you were to do it like this.
Okay.
Look at this, Br is 7 minus 2 bonds minus 1, 2, 3, 4. That's going to give you what? 1, right? Whereas this bromine, that's 7 minus 2, not 2, 1 bond, right? Minus 1, 2, 3, 4, 5, 6. That's 0. Yeah?
Yeah.
Okay, same thing. We need hydrogens, but look at the oxygen. This is why it's got a -1 charge.
The oxygen has 6 valence.
Oxygen has 6 valence.
Minus number of bonds, which is 1.
Because you can't have electrons anywhere else.
Okay. Wait, how many valence did you say oxygen had?
6.
Oh, do you count each electron or you count the pairs?
Each electron.
Oh. So it's 6 minus 1 minus 8? Or, I mean, 6.
So oxygen, its group number is 6 minus 1 bond, right? Minus 6 electrons.
Okay.
So that's a -1 charge.
Wait, is overall charge this? Or is,
Overall charge of, well, the overall charge of this is -1.
oh,
But peroxide This is -2. Nitrite, -3. Ammonium, +1. Carbonate, this. Bicarb, this. Hydroxide, this. Phosphate, cyanide, sulfate.
Wait, did you just memorize that?
Yeah.
But is it because
Googled
like
it.
is overall charge like the formal charges of these like all add up to that?
Yeah, you can, yeah. They all have formal charge of 0. M and X have formal charge of 0. O has a formal charge of -1. Isn't this the same thing? If it's like that, then that means M also has to have like a formal charge, right? So I don't think that's right. Or if it is, it's just not stable. Probably like this. This is 0, 0, 0, 0. If M and X has 0, oxygen has formal charge -1. That cannot work, right? Because we just said that if oxygen is -1 charge, M has to also be a +1 charge.
It all has to add up to 0.
They all have to add up to 0. M and X have formal, yeah. They all have to add up to 0.
Wait, have we done? Oh, we haven't done this, right?
We haven't done this.
So what is bond order?
Bond order is basically like the number of bonds and how many it's basically like how wide these bonds are.
How do you figure it out?
So that's one bond. Where there's a formula. I have to Google it, the formula. Hold on, give me a second. Oh, bond order formula just pops right up. Okay, it's number of electrons in antibonding and number of electrons in bonding. So this one, oh goodness. Number of electrons in bonding minus number of electrons in antibonding. You're like, what the heck is she talking about? Divided by 2. This is the formula, okay? I don't, so oxygen, the way we draw it, I don't know I don't think you guys have done this. Have you guys done molecular orbitals?
Like, what do you mean? Like P, the F?
Like, so you know how oxygen, okay, oxygen, so if you look at, I don't think you guys have done this yet though. Valence of oxygen is 2s2, right? 2p4, right?
Yeah.
So this is oxygen's 2s. This is oxygen 2s, right?
Yeah.
And then we have 2p. So it's 1, 2, 1, 2, 2, 3, 4. Have you guys done this yet or no?
Yeah.
You have?
Yeah.
Okay, good. So you have bonding and anti-bonding. This is the anti-bonding one. So do you see how you have 2 plus 2, that's 4? So if you have 4, you do 1, 2, 3, 4. Okay? You're like,
You have 2s.
form.
Yeah. You have 2s2. How do you have 4?
Because you have 2 of them and 2 of them. So that's
Wait, but
4 electrons.
how do you have 2 of them? How do you have 2 pairs?
Because it's 2s2.
Oh shit.
Yeah. Okay. So now you have sigma, pi, pi antibonding, sigma antibonding, right? And how many do I have here? 4 plus 4, that's 8, right? So I do 1, 2, 3, 4, 5, 6, 7, 8.
Wait, how do you know which ones to put on the top and which ones to put on the bottom?
You always go from bottom level up.
But how do you know which ones are bonding and which ones are anti-bonding?
This is how you draw them. You always draw sigma and then the 2 pi's. Because remember, when you're always doing bonds, the first bond is always going to be sigma, and then after that, it's pi, pi.
Oh, so you just have to memorize how to draw this thing?
Yep, it's drawn that way. And then you count.
And then how do you find?
Oh, wait, hold on. Undo. So then it was number of bonding minus non-bonding, right? So I have 1 that's bonding, 2, 3, 4. 4 that is bonding, minus 1 that is non-bonding, right? Okay. 1 that is anti-bonding. Yep. And then you divide it by 2. This is actually 3 over 2. It's 1.5.
Wait, so there were 4 that were anti-bonding?
Bonding.
Oh, wait, can you just do needed minus available? Because what they're saying.
Needed minus anti-bonding. Like, are you just counting all the electrons?
So it says needed is 16, 2 times 8, then available is 2 times 6. So I get 4.
Hold on, let me see what they're doing. Needed electrons. Okay, yeah. I guess that's the shortcut. Okay. Ethan likes shortcut.
You had me drawing this thing like.
I know. But I think you need to understand it though, either way. Yeah, that's how we were taught. Not this shortcut way. That's hella nice.
For NF3, why don't you put a double bond?
Because you have enough. So that's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We have enough for everyone to be happy.
Wow.
Mm.
Wait, so can we try to do this one using the shortcut that they gave us?
Sure.
Yeah,
So hydrogen needs 2 electrons, right? And we have 2 of them. That means 4 electrons. Carbon needs what? 8 electrons. And we have 2 of them, so it's 16 electrons. So the total is 20 electrons is what we need. How many electrons do we have?
14.
1 plus 4 plus 4 plus 1.
Oh, carbon's 4.
Yeah, carbon only has 4 valence. We only have 10 divided by 2. 5.
Wait, that's not right.
So
though.
wrong.
What? How are they doing it then?
All right, hold on. Let me go back to the thingy. Available electrons. Carbon has 4. Hydrogen has 1. Shared electrons. Needed minus available. Double bond between atoms. Thus the bond order. Therefore, to show this well, as all of these electrons must be shared in the OO bond, and 2 electrons form a single bond. Double bond between the bond order 2. Oh, I know. Okay, go back down to the question. Okay. 5 is the bond order. Okay? But look, we've used 1 and 1.
Oh.
So now we only have 3 that has to go between the carbon and carbon.
Okay.
Yeah. What are we doing here?
Oh, that one you just draw them. It's not that bad.
Oh.
Wait, so you have to balance these things?
Yeah. You want them to be 0 or closest to 0.
Wait, is this formal charge? Or
Those
what are
are
the
the formal charges, yeah.
oh, okay. So resonance, you just move the bond around as much as you can.
Yeah.
Wait, what is the best?
One of these later in Orgo.
What is the best resonance structure?
With the best formal charge.
Best formal charge is closer to 0.
Yeah.
But how is this any better than like having it over here, over here, over here?
There isn't. You never know.
So all the resonance structures are fine.
No, because you can also have it like this. Or you can have it like this.
Uh,
Okay, or you can have them like this. Out of all the different ones, which one is the best one? This one.
wait, why is this? Wait, sorry. Can you put it back?
No. Oh, the
Sorry.
ice. Oh my god. Okay. They just wanted me to draw it.
How is this? Wait, that's fine. You don't have to stop. You don't have to keep drawing. How is this better than that?
Because if you do the formal charges, this is what? 4.
Um, wait, so it's all of these plus P?
Yeah,
Wait, how many valence electrons in P?
5.
So it's 1.
Yep.
And this is 0?
That's 0.
Wait, so are you trying to get the best one for P or for the whole thing?
Usually just for the central atom, and if the central atoms are the same, then you do the rest.
Okay. Wait, when you're drawing resonance structures, you have to draw like a special arrow, right?
Yeah, the double arrow. It actually has been patented just for resonance.
Wow.
I know.
I don't think you know that.
Yeah. It's a whole different level.
Wait, what's polar covalent?
Polar covalent is when they are not, when the vectors don't cancel each other out. So first of all, this is ionic, so you cannot even use it. Cl2 looks like this. So the pool between Cl's are equal to each other, so they cancel each other out. So this is actually non-polar. NH3 looks like this. So there's negative on this side, and then there's positive on this side. So if you were to look at it like a magnet, we have 2 poles.
Oh, okay.
Okay. So remember Hunkelbrief, Brinkelhoff?
Wait, what?
Molecules, Hunkelbrief.
Oh, yeah.
These are all going to be 100% non-polar.
Oh, okay. Wait, how do you find lattice energy again?
So K is a constant. You don't even have to know what that is. These are charges of ions, and these are actually absolute values. So if you look at strontium and S, this is +2 -2, this is +2 -2, +2 -2.
How do you know that?
Because I've memorized it. And then you look at the one that has the smaller radius, okay? And remember, it goes down. So it increases radius as it goes down, right? So we want the smallest radius for it to have the largest lattice energy.
But lowest lattice. So you want the biggest radius?
Yeah.
Oh, so you can just look at the radius because it's getting divided so much.
Because they have the same charges. If they have the same charges, then all you got to do is just look at the radius.
Oh, okay. All right. I
That's
think
it.
that's good. Yeah.
All right. When's your test?
We don't even have tests. We just have quizzes every Thursday.
Oh,
Yeah.
nice life.
Yeah. Well, we have a final, so
Oh,
not anytime soon.
but is that gonna be also Googleable?
I hope.
All right, sounds good. Make sure you ask before you get hit.
Oh yeah. All right.
Yeah.
I'll see you in the next one.
Yeah. All right. Bye.